Good morning, physics class, and welcome to problem set 36, day 3. I believe this will be the last lesson of our year. Next week, we're going to be working on what would normally be the final exam, but instead of it being a final, we're not going to do finals this year, so we're going to work on that as a project, like as an assignment. So here it says that we have 8 amp current passing over 120 ohm resistor. First question is how much voltage goes across the resistor? We've hopefully come to know this and to learn this equation. V equals IR. I like to say volts equals amps times ohms. So in this one we have 8 amps and 120 ohms is going to give us how many volts are passing over the resistor. So again, we have 8 times 120 equals 960 volts. Okay. Then it asks the power output of the voltage source. Well, we've learned that power equals I squared R. We've also learned that power equals V times I. But because I chose this equation because I was given amps and ohms in the problem. So the amps is 8 amps, so I'm going to square that, and then I'm going to multiply it by 120 ohms in order to get the power. So let me erase that, fix that. That looks kind of strange. So P equals 64 times 120. 64 times 120 equals 7,680 watts equals P. All right, so the answers I'm going to put, two significant digits, V equals 960 volts, and P equals 7,700 watts. There we go. There's our two solutions. All right, now here we go. It says the velocity of a particle is described by the equation 6x cubed minus 32x squared plus 2x minus 800. Find the position after 12 seconds, the particle after 12 seconds, and the acceleration after 12 seconds. So what I'm going to remember is that first I've got the equation of velocity over x equals 6x cubed minus 32x squared plus 2x minus 800. All right, I'm going to go up to position at 12, and this has to be at 12, and we're down to acceleration. Remember, x v a is the derivative, dy dx, and going up is the integral, okay? So if we're going up to position, we're going to use the integral, so that's going to be 6x to the 4th divided by 4 minus 32x cubed over 3 plus 2x squared over 2 minus 800x plus the constant. And we don't have a constant, so we could just make that 0 in this particular problem. We're assuming that it's 0. All right, for the derivative, we're going to say that this is 18x squared minus 64x plus 2. And again, we're going to plug 12 into all of them. So the first one it asks for is position. So let me get out of blue here, and we'll say x at 12 seconds is 6 times 12 to the 4th over 4 minus 32 times 12 cubed over 3 plus, and I could just say the 2's cancel, so I could just say that that's 12 squared, right? Like think that would work. Minus 800 times 12 plus 0, because we aren't given a constant. All right, let's begin working that out. We'll do exponents first. So 12 to the fourth is 20,736 times 6 divided by 4 is 31,104 minus 12 cubed times 32 divided by 3 gives me 18,432 plus 144 minus 800 times 12 is 9,600. So I can combine like terms. 31,104 minus 18,432 plus 144 minus 9,600 gives me a grand total for the position after 12 seconds is 3,216 units. We don't know what the unit is. We don't know if it's meters, centimeters, inches, feet, so we're just going to put units, okay? All right, now let's work on velocity. So for velocity, we're going to say it's 6 times 12 cubed minus 32 times 12 squared plus 2 times 12 minus 800. So 12 cubed is 1,028 times 6 is 10,368 minus 144 times 32, which is 4,608 plus 24 minus 800. So 10,368 minus 4,608 plus 24 minus 800 gives me a velocity at 12 seconds of 4,984 units per second. All right, now we're going to work on acceleration at 12 seconds, which is going to be equal to 18 times 12 squared minus 64 times 12 plus 2. So we got 12 squared. 18 is 2,592 minus 64 times 12 is 768 plus 2. So 2,592 minus 768 plus 2 equals 18. So the acceleration at 12 is 1826 units per second squared. I've got 2 significant digits in the problem from 2 and 2. So I'm going to go with x at 12 is 3,200 units. V at 12 is 5,000 units per second. And acceleration at 12 is 1,800 units per second squared. So I came up with 3 answers there. Hopefully you'll be ready for this on this week's test. Okay. Some college students are given the task of boiling 24 grams of mercury that currently has a temperature of 31 degrees Celsius. How much energy needs to be consumed? If I'm going to do a problem like this, the first thing that I need to do is I need to consult the specific heat chart that was given to you last week. I believe it was last week, or it might have been a couple weeks ago. And once you have consulted that, you can begin to calculate this out. So the first thing that I want to do is I want to look up the specific heat of mercury. The specific heat of mercury, I looked it up on the chart. I just pulled my chart out here, and I see that it's 140 joules per kilogram degrees Celsius. And it says here 24 grams, and I know that there are 24,000 grams because there's 1,000. Sorry, I didn't do a proper unit analysis on that. Hope you'll forgive me. And I also want to find the change in degrees Celsius. Please don't, when I talk about the change in degrees Celsius, please don't put 31 in there. We want to boil this, so we need to find out how many degrees it takes to boil it. So the change in degrees Celsius from the 31 degrees that we start at to go up to the 357 degrees, which is the boiling point, which I also found on that little chart that I gave you. So I take 357 minus 31 equals 326 degrees Celsius. That's the change. So 326 degrees Celsius will cancel, and my kilograms will cancel, and the only thing that's left is joules. So I got 140 times 24,000 times 326. Ooh, gives me a big number. I didn't realize it was going to be that big. 109,536,000. So, a billion joules is what it would take to take 24. Good night. No, we got to go back to the drawing board. You remember when I said, hey, we don't skip steps? I should never skip a step. And I did. So we got to go all the way back to the drawing board here because what I've got is 24 grams. And they're actually 1,000 grams per 1 kilogram. And so in order to solve that, I should have done the proper unit analysis. I didn't, and I got a little too quick there. And so the change in degrees Celsius, excuse me. So that's why it's so important to do out everything in our unit analysis. To go from 31 degrees to 357, I believe it was 357 degrees Celsius. 357 minus 31 equals 326. 326 degrees Celsius. So degrees Celsius cancel. My grams cancel. My kilograms cancel. Now we should be in business. 140 times 24 times 326 divided by 1,000 gives us 1,095.36 joules. Okay, that sounds like a more reasonable, because we're not dealing with pounds of mercury. So this sounds more like it ought to be. I'm glad I double kind of checked there. All right, now the next thing we want to do is we want to see what it's going to take to boil that. It also takes a large amount of energy to boil it. So the heat of vaporization of mercury is 227,000 joules per kilogram. And like I said before, I've got 24 grams, and we know that there are 1,000 grams per kilogram. I was just thinking back to it. I've been a stickler on unit analysis all year, and the one time here that I kind of skipped something, we saw how it really led me down a wrong road. And I've seen many of you on your tests, on your problem sets, where you've done little things like that and you've made similar mistakes. I couldn't have scripted that better if I tried to do this. All right, so we're going to take 272,000 and we're going to multiply by the 24 grams, and then we're going to divide by the 1,000 grams that we have in order to get that it would take 6,528 joules in order to boil that mercury. So then we'll add it to the 1,095.36 joules it took to raise the temperature from 31 degrees Celsius to the boiling point of 357 degrees Celsius to get a grand total of 7,623.36 total joules of heat energy in order to boil this mercury. Okay, so now if we were to take and we were to put that into significant digits, I see that there's 2 significant digits in the problem. We're going to get 7,600 total joules of energy, right? Let's keep moving on. An observer hears a cannon fire. Kaboom! And draw my cannon. Okay. And he hears his cannon fire, and he sees the flash from the cannon. Oh, I gotta need a cannonball. And he hears the sound 11.4 seconds later. 11.4 seconds. Hopefully he's not in the direction of the cannon. All right. Great hunter. That was left over from a slide that I've only kind of manipulated. The speed of light is 3 times 10 to the 8th meters per second. The speed of sound is 350 meters per second. How far is he away? So if it's 350 meters per second, and he hears it 11.4 seconds later, simple unit analysis will say 350 times 11.4 equals 3,990 meters. Now let's say we knew the meters, like we said, oh, he's 4.5 kilometers away. Hypothetically, please don't think that this is part of the question. I could take those kilometers and divide by the seconds to find the speed of sound on a particular day. Take that in a note. That might play into something you're going to do later on. You can also, in other words, you can also use this same unit analysis to work this backwards. Having done the homework and the quiz, I want to alert you to that I might change things up on you. So be ready. I'll be able to tell if you watch this video or not when it comes quiz and test time. All right? Because if I get people saying, Mr. Wilson, you never talked about that, I'd say, I just did. I did in the video. All right? So, anyways, if we were to say that we know that the speed of light is 3.00 times 10 to the 8th meters per second, and we were to take our 3,990 meters, and then we were to use a little bit of flipping the formula unit, 300 times 10 to the 8th meters per 1 second. We could find out how fast he would see this happen. So we can take our, again, 339 and divide by 3 times 10 raised to the 8th power. And excuse me, I hit that wrong. Let me try over. 3990 divided by 3 times 10 raised to the 8th raised to the 8th power. There, got it. Okay. You'd see it 1.3 times 10 to the negative 1, 2, 3, 4, 5th seconds. Okay, but the answer we are looking for, it says how far was he away? I would say that he was 2 significant digits, 4.0 times 10 to the 3rd meters away. All right. Well, we're all done with our slides for today. Getting ready for the last test of the year. Hope to see you soon. Talk to you later. Goodbye.